28 revolutionary space missions vanished without a trace. You will discover the secret technologies they carried and how their disappearance altered our future. Why did a Soviet probe with a plasma spectrometer burn up before reaching Mars? What happened to the advanced ion engine that could have traveled time to the outer planets? These silent sentinels hold stories of ambition and loss that still echo today. What do you believe is the greatest cost of reaching for the stars? A plume of smoke and fire marked the end of a dream before it even left Earth. The Soviet Union's Mars 4M No. 522 probe sat atop its Proton rocket in 1971, a technological jewel packed with ambition. Its primary instrument was something never before sent to another world, a plasma spectrometer designed to read the very soul of the Martian atmosphere. This was not just another camera or soil sampler. It was a key that could unlock the planet's deepest secrets, analyzing the composition and behavior of its thin air with a precision thought impossible at the time. Scientists believed the data could reveal early clues about the planet's ancient climate and even its potential, however faint, to have once supported life. But that key was never turned. A malfunction in the rocket's upper stage condemned the probe to a swift and brutal death, burning up in the dense layers of our own atmosphere. The loss was more than a single mission failure. It was a setback that echoed for decades. Without that specialized sensor, our understanding of Martian climate cycles remained fragmented and incomplete. Subsequent missions, both Soviet and American, simply did not carry the same revolutionary tool. This left a gaping hole in our knowledge, one we are only now beginning to fill. The probe itself was a marvel of solar-powered engineering, yet its development was rushed under immense political pressure. The Cold War space race demanded milestones, not meticulousness, and in that frantic environment, a technological masterpiece was sacrificed. One has to wonder, how much sooner would we have pieced together the story of Mars's watery past if that single, silent sentinel had made it to its post? This first great loss set a somber pattern, a pattern we see repeated with a different kind of engine far from the red planet. While one probe burned in the atmosphere, another never even felt the cold of space. In a clean room in the 1970s, NASA Pioneer H stood complete, a finished spacecraft with nowhere to go. Its mission was not to orbit a planet or photograph a moon, but to prove a revolutionary concept, the ion engine. This was not the fiery, explosive thrust of chemical rockets. Instead, it worked on a principle of elegant efficiency, using solar power to electrically charge atoms of xenon gas and then shooting them out the back at incredible speeds. The push from each individual ion was minuscule, but it could be sustained for months, even years, building up velocities chemical engines could never achieve. This was the key to the outer solar system, a technology that promised to slash journey times to Jupiter and Saturn by half. Yet Pioneer H never left its warehouse. Political winds shifted, budgets tightened, and the unglamorous work of proving a new propulsion system was deemed expendable. The probe was eventually donated to a museum, a silent monument to a road not taken. The true cost of that decision is staggering to consider. Without the pioneering data from a dedicated test flight like Pioneer H, the development of practical ion propulsion was delayed by decades. Space historians often point out that this lost mission could have provided the crucial confidence needed to use such engines on larger, crewed vessels to asteroids, accelerating our reach into the cosmos by a generation. Its story is a quiet cautionary tale, a reminder that progress is not a straight line but a fragile path easily abandoned. How many other breakthroughs are sitting in forgotten archives, waiting for their moment to fly? This pattern of terrestrial failure would soon be followed by a mystery far out in the void. A successor to the star mapper Hipparcos was already taking shape on engineers' drafting tables, a spacecraft called Hipparcos 2. Its proposed hyperspectral imaging technology was a quantum leap beyond its predecessor, designed not just to chart stars but to build a three-dimensional map of the Milky Way with a precision down to mere millimeters. This was not a simple star chart, it was a galactic blueprint. With such phenomenal accuracy, its sensors would have been sensitive enough to detect the faintest wobble in a star's position, the telltale signature of an unseen planet's gravitational tug. Astrophysicists are confident Hipparcos 2 could have identified hundreds, perhaps thousands, of these exoplanets years before dedicated planet hunters like Kepler began their work, fundamentally reshaping our search for habitable worlds far earlier. But the mission was never built. In the early 2000s, funding was reallocated, and the ambitious project was scrapped after its initial design phases. The cancellation left a void in our understanding of our own galactic neighborhood, forcing scientists to rely on less accurate data for years. This was a loss driven not by a rocket's failure, but by a balance sheet, a stark reminder that financial constraints can eclipse the brightest scientific potential. The echoes of such terrestrial decisions would soon be heard in the silent, airless void around another world. The silence of a cancelled blueprint was soon followed by the quiet despair of a machine that flew but could not see. In 1997, Japan's HALCA satellite soared into orbit, carrying the hopes of radio astronomers worldwide. Its mission was audacious: to create the first space-based very long baseline interferometer. This was not a single giant dish, but a revolutionary network linking the satellite with telescopes on Earth to form a virtual observatory the size of our planet. The resulting resolution was staggering, promising to peer into the hearts of distant galaxies and image the immediate surroundings of supermassive black holes with a clarity never before imagined. Scientists were poised to see the unseeable, to capture the shadow of a black hole's event horizon decades before the Event Horizon Telescope project made headlines. But that vision was never realized. A critical antenna, essential for receiving the faint whispers from the cosmos, failed to deploy correctly. HALCA was stranded in orbit, a deaf ear turning endlessly in the void, its revolutionary receiver rendered useless. The loss was a profound blow to fundamental physics. Experts have since reflected that the data from HALCA's full mission could have provided early, indirect evidence of gravitational waves, the ripples in spacetime predicted by Einstein. This could have predated the ground-breaking confirmations from the LIGO Observatory by years, accelerating our understanding of the universe's most violent events. HALCA's story is a stark lesson in the fragility of complex ambition, where a single stuck component can silence a symphony of discovery. It reminds us that in the unforgiving environment of space, success and failure are separated by the thinnest of margins. This delicate balance would be tested once more, not by a mechanical fault, but by an invisible and relentless force from the depths of the galaxy. High above the Earth, a ghost satellite drifted silently, its memory banks wiped clean. The United States Space Test Program 86-1 was a product of its time, born from the intense technological rivalry of the Strategic Defense Initiative. Its cargo was not a weapon, but something almost as valuable, a pair of experimental laser communication terminals. This was not radio, with its easily intercepted and relatively slow data streams. This was focused light, capable of transmitting vast amounts of information, from complex sensor readings to real-time high-definition video, across the vast emptiness between spacecraft. Imagine receiving a live, crystal-clear feed from a probe orbiting Jupiter as if you were looking out a window. That was the future this satellite promised. But that future was erased by a single, catastrophic software error. Shortly after its launch in 1986, an onboard computer glitch triggered a system reset that cleared its core programming. The satellite was left brain dead, a perfectly functional body with no mind, its revolutionary laser transmitters forever silent. Because the mission was highly classified, the full extent of its capabilities and the precise nature of the failure remained locked away for years. This secrecy compounded the loss, as the broader scientific and engineering community could not learn from the mistake. The setback delayed the maturation of laser comms for both military secure links and civilian deep space exploration by a generation. We are only now, decades later, beginning to deploy similar systems. The silence of STP-86-1 forces a difficult question. How many other technological leaps have been lost not to explosions or cosmic rays, but to vaults of classification and erased memory? Sometimes, however, the loss is not due to a glitch or a secret, but to a simple, heartbreaking miscalculation. A perfect launch gave no hint of the silence to come. India's GSat-6 satellite soared into the sky in 2018, a symbol of national ambition carrying a revolutionary piece of hardware. Its 6-meter-wide antenna was the largest ever deployed by an Indian spacecraft, an umbrella of advanced mesh designed to unfurl in the vacuum of space. This was not just about more television channels, it was about connection. The satellite's sophisticated adaptive beam-forming technology could focus powerful mobile broadband signals directly into India's most isolated villages and rugged terrain, places where laying cable was impossible. It promised to bridge a vast digital divide, bringing education, healthcare, and economic opportunity to millions who had been left in the informational dark. For a brief moment, everything worked. The launch was flawless and initial communications were strong. Then, after a planned maneuver, the signal simply vanished. A catastrophic power failure, likely a short circuit in the electrical bus, had plunged the advanced satellite into darkness, permanently severing its connection to Earth. The loss was a brutal lesson in the fragility of complex systems. Engineers later reflected that while the satellite's technology was cutting edge, its power system redundancy may not have been robust enough to survive such a fault. The silence from GSat-6 forced a complete rethink of backup systems in future designs, a costly but necessary evolution born from failure. The human cost, however, is the hardest to quantify. How many students in a remote village lost their chance at online learning? How many clinics were denied a telemedicine link that could have saved lives? This failure reminds us that behind every lost signal, there is a ripple effect of human potential left unfulfilled. Such a sudden, complete silence is a haunting echo of another mission that simply ceased to be. The silence from Earth orbit was a prelude to a far more ambitious failure. Russia's Phobos-Grunt mission launched in 2011, a bold endeavor to achieve what no one had before, to land on the mysterious Martian moon Phobos, scoop up a sample of its soil, and bring that precious cargo back to Earth. This was not a simple grab, it was a sophisticated ballet of autonomous technology. The lander carried a novel drilling system designed to operate entirely on its own, far from any human control, collecting material from that distant, alien surface. Even more revolutionary were the onboard isotopic analyzers, miniature laboratories that could have dated the very rocks it collected. These instruments were the key to unlocking the origin of Phobos itself, potentially proving whether it was a captured asteroid or a piece of Mars blasted into orbit by a colossal impact. The answers were right there within its robotic grasp, but they were never reached. A catastrophic propulsion failure left the spacecraft stranded in a decaying orbit around our own planet. For weeks, it tumbled helplessly, a billion-dollar promise of discovery slowly circling closer to a fiery doom. The world watched as Phobos-Grunt burned up in the atmosphere, its unique instruments and the secrets they held turning to ash over the Pacific Ocean. The loss was a devastating blow to planetary science, setting back sample return ambitions by more than a decade and leaving the fundamental question of the Martian moon's birth unanswered. Its story is a stark, humbling lesson in the unforgiving precision required for interplanetary travel, where a single error in the first few minutes can erase years of work and infinite potential. This tragedy of a mission that never left home serves as a sobering prelude to another spacecraft that flew, but whose revolutionary method of travel was never fully proven. The dream of sailing on sunlight died with a faulty rocket. In 2005, the Planetary Society's Cosmos 1 spacecraft was poised to make history as the first successful solar sail in orbit. This was not a mission backed by a national space agency with a massive budget, but a project fueled by the passion and donations of private citizens, a true grassroots effort to push the boundaries of exploration. Its design was elegantly simple yet profoundly ambitious, a spacecraft propelled not by fuel but by photons. Imagine a vast, incredibly thin mirror, catching the faint but constant pressure of sunlight itself. That continuous push, minute on its own, could theoretically accelerate a vessel to immense speeds over time, enabling journeys across the solar system without a single drop of propellant. Cosmos 1 was built to prove that very principle, its 8 triangular sails of reflective mylar waiting to unfurl like a giant flower in the void, but that flower never bloomed. A failure in its Volna launch vehicle condemned the spacecraft to a fiery end, plunging back into the atmosphere before it could even reach the starting line. The loss of Cosmos 1 was more than the failure of a single experiment. It was a setback for an entire concept of travel. Proponents of solar sailing argue that a successful demonstration could have spurred immediate investment, potentially accelerating missions to the asteroids or the outer planets by years. Instead, the technology was shelved, its practical testing delayed for over a decade until the Japanese Hipparcos probe finally succeeded in 2010. This mission embodies the unique perils of public-private partnerships, where monumental dreams can be extinguished by a single, mundane mechanical fault. It makes you wonder how many other revolutionary ideas are waiting in the wings, their progress stalled not by a lack of imagination, but by the immense risk and cost of just getting off the planet. This grassroots loss stands in stark contrast to the next failure, a deeply secretive mission that carried a different kind of revolutionary cargo, one intended not for the light of the sun, but for the shadows of the moon. A guidance error can erase a triumph in an instant. China's Chang'e 5T1 mission in 2014 was a crucial test flight, a dry run for an ambitious lunar sample return. Its primary goal was to validate the complex process of swinging around the moon and hurling a capsule back toward Earth. In that, it was a stunning success, proving the trajectory and navigation were sound. But the mission carried a hidden revolutionary component, an experimental re-entry capsule equipped with a heat shield made of entirely new composite materials. These were not the standard ablative shields that burn away, but advanced structures designed to withstand the blistering heat of a high-speed return from deep space, the kind of velocity a mission from Mars would experience. As the capsule screamed back into the atmosphere, it was a flying laboratory, its skin instrumented to record every detail of its trial by fire. Then the guidance error struck. A slight miscalibration caused the capsule to enter at a less than ideal angle, and during this critical phase, a key telemetry link failed. The precious stream of data on how the new materials were performing was corrupted, a garbled mess of incomplete readings. The capsule itself landed safely, a physical success, but its most valuable secret, the performance data of the shield, was lost. Aerospace engineers have lamented that this specific, high-velocity re-entry data was a unique treasure. It could have directly informed the design of heat shields for future crewed missions to Mars, providing real-world validation that computer simulations simply cannot match. Without it, planners were forced to rely more heavily on those simulations, adding a layer of uncertainty to the most dangerous part of a journey to the Red Planet, the fiery return home. This incident stands as a powerful lesson in how a mission can be both a success and a profound loss, where a single, small error can rob us of knowledge that might have protected human lives on the next great voyage. It forces us to confront the immense difficulty of just getting a spacecraft home in one piece, a challenge that would soon be faced and failed by an entirely different kind of explorer. A software bug can turn a perfect approach into a near collision. In 2005, aboard the Space Shuttle, NASA conducted a critical experiment called the Demonstration of Autonomous Rendezvous Technology, or DARE. Its goal was audacious: to prove that two uncrewed spacecraft could find each other and dock in the vast emptiness of orbit, entirely on their own. This was not just about convenience, it was the foundational technology for a future of robotic mechanics in space. The system relied on a sophisticated combination of LiDAR, which uses laser light to map its surroundings in precise detail, and early machine learning algorithms designed to make real-time decisions. Imagine a future where a service satellite could autonomously rendezvous with a failing telescope, dock with it, and replace a faulty component, extending its life for years. DARE was meant to be the first crucial step toward that reality. During the test, the shuttle released a small target satellite, then began a carefully choreographed dance to approach it using only its autonomous systems. For a while, it worked perfectly. Then, a subtle flaw in the software's logic caused it to misinterpret the data from its LiDAR. The system began to believe the target was much closer than it actually was, triggering an emergency abort just as the shuttle was about to demonstrate the final, critical docking maneuver. The mission was safe, but the experiment was a complete loss. The most valuable data, the validation of the final approach and contact algorithms, was never gathered. Robotics experts point to this failure as a major setback. Without the confidence gained from a successful DARE test, the development of on-orbit servicing and assembly was delayed by years. The technology had to be revalidated through slower, more expensive ground tests and smaller, less ambitious orbital demonstrations. This single software glitch highlights an enduring tension in space exploration: the delicate balance between the incredible potential of full automation and the absolute necessity of reliable, fault-proof oversight. It forces a difficult question: how much trust can we place in the cold logic of an algorithm when a single misread number can spell disaster? This invisible threat of digital error would soon be joined by an even more insidious and powerful force, one that strikes from the depths of the galaxy itself. A perfect launch can still lead to a useless orbit. The European Space Agency's Artemis satellite lifted off in 2001, its name evoking the goddess of the hunt, yet its true mission was one of connection. It was built to demonstrate a revolutionary technology: laser inter-satellite links. This system was designed to create a network of beams, invisible threads of light connecting spacecraft across the void, capable of shuttling immense amounts of data at speeds that made traditional radio seem like a whisper. This was the blueprint for a new kind of orbital infrastructure, one that could relay information from a remote sensing satellite over the Atlantic to a ground station in Europe in an instant, or form the backbone of a global space-based internet. But Artemis never got to test its eyes. A malfunction in the upper stage of its Ariane 5 rocket left the satellite stranded in a low, elliptical orbit, a graveyard loop far from its intended geostationary perch. For weeks, ground controllers fought a desperate battle, using the satellite's own tiny thrusters and every last drop of its precious hydrazine fuel to nudge it, inch by painstaking inch, into a marginally more useful orbit. It was a monumental feat of engineering salvage, but the primary mission was already lost. The delicate optical communication payload, the very heart of its revolutionary purpose, was rendered useless at the wrong altitude. The loss of Artemis created a years-long delay in the maturation of laser data relays. Telecom historians often note that a successful demonstration in 2001 could have accelerated the entire industry, potentially spurring the deployment of global internet constellations a decade earlier than we saw them. Its story is a masterclass in the brutal precision of orbital mechanics, where an error of a few meters per second at the right moment can invalidate billions of dollars and years of work. It proves that in space, getting almost everything right is still a form of failure. This terrestrial struggle to reach the correct orbit sets the stage for a far more profound disappearance, one that occurred not around our world, but on a distant journey to a silent rock. Japan's blueprint for an asteroid hunter was shelved before it could ever fly. The Hayabusa Mark II was conceived as the direct successor to its trailblazing namesake, a spacecraft designed not just to repeat a success, but to perfect it. Engineers envisioned a more robust and powerful ion engine, one that could push the probe to multiple asteroids within a single mission. Its most revolutionary tool, however, was a miniature rover, a tiny robotic scout designed to detach and hop across the alien terrain of a small world. This was not a static lander, it was a mobile explorer capable of seeking out the most scientifically interesting samples before the mothership descended to collect them. The autonomous navigation systems required for this delicate dance represented a quantum leap in robotics, a step toward truly intelligent probes that could think for themselves in the deep void. Slated for a launch in the 2010s, the Mark II promised to turn sample return from a spectacular gamble into a reliable, repeatable science, but that promise evaporated. In the face of tightening budgets and shifting national priorities, the entire program was cancelled during its planning stages. The loss created a void in small body exploration that lasted for years. Space resource researchers often point to the Hayabusa Mark II as a pivotal missed opportunity. The advanced techniques it was meant to prove, from precise autonomous landing to on-site analysis, are the very same skills required for the future mining of asteroids for water and precious metals. Its cancellation didn't just delay a scientific mission, it pushed back the entire timeline for developing a space-based economy, a delay we are still working to overcome today. The story of the Mark II is a quiet tragedy of ledger books and balance sheets, a reminder that the most advanced technology is useless if it never leaves the drawing board. This terrestrial failure, born from financial pressure, stands in stark contrast to the next kind of loss, one caused not by accountants, but by the violent and unpredictable fury of our own sun. The silent drift of a brain-dead satellite was followed by a different kind of disappearance, one born from a routine procedure gone horribly wrong. In 2014, NASA lost contact with its Stereo-B spacecraft, a solar observatory on a monumental mission. Along with its twin, Stereo-A, it was equipped with revolutionary heliospheric imagers, instruments that for the first time allowed scientists to see coronal mass ejections in 3 dimensions. These aren't just solar flares, they are billion-ton clouds of magnetized plasma hurled from the sun at millions of miles per hour. Stereo B's unique vantage point was essential, providing the depth perception needed to accurately track these storms as they raced toward Earth. The loss occurred during a planned test, as the spacecraft entered a period of solar conjunction when the sun itself blocks communication with Earth. Engineers commanded a system reset to ensure it would recover automatically. But the reset contained a hidden flaw. A timing error in its recovery software left the spacecraft disoriented, causing it to spin uncontrollably. Its solar panels drifted away from the sun, its batteries drained, and its advanced sensors, tuned to watch the sun's fury, were plunged into permanent silence. For years, NASA listened for any faint signal, a whisper from the void, before finally declaring the mission over. The consequence of that single software anomaly was immense. Space weather forecasters were suddenly left with only one eye on the sun, Stereo A, drastically reducing their ability to predict the trajectory and strength of incoming solar storms. These predictions are not abstract science. They are vital for protecting our technological civilization. A precise warning allows satellite operators to put their assets into safe mode, and for power grid managers to brace for potentially devastating geomagnetic currents. Without Stereo B's stereo vision, our forecasts became less certain, leaving our infrastructure more vulnerable to a direct hit from a solar hurricane. This incident is a stark lesson in the fragility of our deep space communication links, where a single, well-intentioned command can orphan a billion-dollar sentinel. It highlights how our reach into the cosmos is always tempered by the relentless, unforgiving physics of the void, a theme that would soon play out in a much more crowded and dangerous environment, Earth orbit itself. Its 10-meter antenna was a silent ear turned toward the heart of the galaxy. Russia's Spektr-R, launched in 2011, was not just another satellite, it was the core of a revolutionary instrument known as Radio Astron. By linking its enormous dish in space with a global network of radio telescopes on the ground, it created a virtual observatory with a diameter as wide as the Earth itself. This gave it an angular resolution so phenomenally sharp it could, in theory, spot a coin on the surface of the Moon. Its primary targets were the most energetic objects in the universe, the supermassive black holes at the centers of distant galaxies, and the mysterious, high-speed jets of plasma they fire into the cosmos. Scientists were poised to see the launch mechanisms of these jets with a clarity never before possible, to understand the very engine that powers some of the universe's most violent phenomena. For years, it delivered breathtaking data, pushing the boundaries of what we thought we could see. Then, in 2019, the communications began to fail. Commands from Earth went unanswered, and the steady stream of cosmic whispers fell silent. The satellite systems, aged beyond their planned lifespan, had finally succumbed to the relentless harshness of the space environment. A last-ditch effort to re-establish contact failed, and the mission was declared over. The loss was a profound blow to fundamental astrophysics. Astronomers note that Spektr-R was on the cusp of providing definitive evidence to distinguish between competing theories of how black holes accelerate matter to near light speed. Its unique, ultra-high-resolution view was irreplaceable, and its demise left a gaping hole in our observational capabilities that has yet to be filled. The story of Spektr-R is a quiet tragedy of entropy, a reminder that even our most brilliant robotic sentinels are ultimately mortal, their revolutionary work cut short not by a single explosion, but by the slow, silent creep of time and cosmic radiation. It forces us to ask, how do we build for longevity in a realm designed to break things down? This challenge of sustaining our assets in the void stands in stark contrast to the next loss, where failure was not a slow decay, but a sudden, violent end tied to a bold new way of moving through space. A power system is a spacecraft's beating heart, and when it fails, the most brilliant eyes are blinded. The United States Air Force's MightySat 2.1 launched in 2000. Its mission to demonstrate a sensor so advanced it could read the chemical signature of the Earth itself. This was not a simple camera, it was a Fourier transform hyperspectral imager. In plain terms, it did not just see colors as we know them, it could distinguish between hundreds of subtle shades of light, each one a unique fingerprint for a specific material on the ground. Imagine flying over a mountain range and instantly identifying deposits of copper, lithium, or gold just by the specific way sunlight reflected off the rocks. That was the revolutionary promise of MightySat. It could map resource wealth from orbit with a precision previously confined to laboratory samples, transforming prospecting from a ground-based gamble into a targeted science. But that vision never materialized. Mere days after reaching orbit, a catastrophic failure in the satellite's electrical bus starved the advanced imager of power, silencing it forever. The satellite itself became just another piece of silent space junk, its unparalleled sensor now useless. Remote sensing experts have long pointed to this loss as a pivotal setback. The data from MightySat 2.1 could have validated this hyperspectral technology years earlier, accelerating its adoption for commercial mining, agriculture, and environmental monitoring. Instead, the industry had to wait, the potential for a global resource map delayed by a single, mundane electrical short. It is a stark lesson in spacecraft design, where the most sophisticated payload is utterly dependent on the reliability of its most basic systems. This pattern of a single point of failure would soon be repeated in a far more dramatic fashion, as another spacecraft prepared for a maneuver that would seal its fate. A satellite can be a lifeline for an entire region. India's INSAT-4B launched in 2007. Its mission was to illuminate South Asia with information. It carried a suite of high-throughput Ku-band transponders, a technical term for powerful, focused radio channels designed to deliver crystal-clear direct-to-home television and high-speed internet directly to dishes on people's roofs. This was not just an upgrade, it was a digital revolution in orbit, promising to connect remote villages and bustling cities with equal ease, but that promise was cut in half. A sudden and irreversible partial power failure struck the satellite, crippling its electrical systems. It did not go completely dark, but it was left operating at a fraction of its intended strength, as if a mighty river had been reduced to a trickle. The loss of half its bandwidth was a severe economic and social blow. Telecom analysts have since reflected that at full capacity, INSAT-4B could have accelerated the rollout of broadband and digital television across the Indian subcontinent by years, bringing educational content, business opportunities, and essential services to millions sooner. Instead, the impairment forced a costly and hurried launch of replacement satellites, straining national budgets and delaying the digital empowerment of an entire generation. This failure stands as a sobering lesson in the high stakes of commercial space, where a single electrical weakness can dim the future for millions on the ground. It highlights a brutal truth that in our interconnected age, a satellite's malfunction is not just a technical problem, it is a human one. This story of a crippled communication hub sets the stage for a far more dramatic failure, where the stakes were not just connectivity, but the survival of a spacecraft on a distant, dusty plain. A flawless descent can be undone by a single line of flawed code. The European Space Agency's Schiaparelli lander separated perfectly from its mothership in October 2016, beginning a silent, 6-minute plunge toward the rusty soil of Mars. Its mission was not just to land, but to prove a new generation of smart landing technology. At its heart were two revolutionary systems working in concert: a Doppler radar to constantly measure its exact velocity and altitude above the terrain, and a sophisticated inertial measurement unit tracking every twist and turn of its descent. This was the blueprint for a precise, automated touchdown, the kind of gentle, guided landing essential for future missions aiming to retrieve samples from the Martian surface and launch them back to Earth. For 4 of those 6 minutes, everything was perfect. Then, a subtle but catastrophic software glitch occurred. The inertial measurement unit became saturated with data during the parachute deployment, a condition the flight software misinterpreted. For a single, fatal second, the computer believed the lander was already below ground level. It responded by instantly jettisoning its parachute and backshell far too early, firing its braking thrusters for only 3 seconds instead of the planned 30, and then switching off, convinced it had landed. In reality, Schiaparelli was still 2.5 miles above the surface. It fell the rest of the way in silence, impacting at over 300 kilometers per hour and scattering its experimental sensors across the Martian plains. The loss was a brutal lesson in the unforgiving nature of automation. Mars exploration teams have since stressed that a successful Schiaparelli landing would have provided the crucial confidence needed to scale up these systems for the much heavier, more complex rovers required for a sample return campaign. Without that validation, engineers were forced back to the drawing board, relying on older, more conservative landing methods and necessitating years of further, costly testing. This single software anomaly didn't just destroy a lander, it set back the entire timeline for one of planetary science's most ambitious goals. It forces a humbling reflection that our most advanced robotic explorers navigate alien worlds on a knife's edge, where a misinterpreted sensor reading can erase years of work in an instant. This high-stakes gamble on a distant world stands in stark contrast to a failure that occurred before the journey even began, a mission claimed not by a software bug, but by the raw, explosive power of a launch anomaly. The thin metal skin of a rocket fairing is all that stands between a billion-dollar dream and the violent fury of ascent. NASA's Glory satellite learned this brutal lesson in 2011, a climate sentinel packed with revolutionary polarimeters. These were not ordinary cameras, they were hypersensitive instruments designed to measure the precise way sunlight scattered through tiny particles in our atmosphere, known as aerosols. Understanding these aerosols was the key to one of the largest uncertainties in climate science. Some aerosols, like sulfates from pollution, reflect sunlight back into space and cool the planet. Others, like black carbon from fires, absorb heat and warm it. Glory's unique sensors were built to distinguish between these types on a global scale, creating a definitive map of their influence. This data was poised to refine global warming predictions by a significant margin, giving humanity a clearer picture of its future. But that clarity was lost to the sea. Minutes after a picture-perfect launch from Vandenberg Air Force Base, a command to separate the rocket's nose cone failed. The fairing, designed to protect the satellite during its climb through the thick lower atmosphere, simply never opened. With its aerodynamic shield still clamped shut, the Taurus XL rocket could not reach orbit. It succumbed to gravity and drag, plunging Glory and its irreplaceable instruments into the cold, dark waters of the southern Pacific. The loss was a devastating blow to climate modeling. Scientists have since lamented that the continuous record Glory was meant to provide would have been the gold standard, a baseline against which all other measurements are compared. Without it, a critical gap exists in the long-term data on how aerosols are changing, forcing modelers to rely on a patchwork of less capable instruments. This single structural failure underscores how the entire fate of a mission, years in the making, can hinge on a single, simple mechanical action that never happens. It is a stark reminder that the journey to space is a gauntlet of precisely timed events, where the failure of one can erase the purpose of all the others. And sometimes the peril is not in the violent ascent, but in the quiet, persistent drain of power long after a spacecraft has reached its post. A single flawed line of code unraveled a $2.5 billion dream. Japan's Hitomi satellite, also known as Astro-H, was a masterpiece of X-ray astronomy, a silent observatory designed to listen to the most violent whispers of the universe. Its revolutionary heart was an array of microcalorimeters, instruments so sensitive they could measure the individual energy of each X-ray photon striking the detector. This was not merely taking pictures, it was reading the cosmic fine print. With this phenomenal resolution, Hitomi was poised to perform high-resolution spectroscopy on the superheated plasma swirling at the edge of black holes and within vast galaxy clusters. It could have measured the turbulent motions and chemical composition of this million-degree gas with a precision never before achieved, revealing how black holes influence the growth of entire galaxies. For a brief, shining month in 2016, it worked, sending back data that left astrophysicists breathless with its clarity. Then the satellite began to spin. A cascade of errors in its attitude control system, triggered by faulty software that misinterpreted the spacecraft's rotation, commanded the thrusters to fire in exactly the wrong direction. The corrective pushes only made the spin faster and faster, until the immense centrifugal forces tore the satellite apart. Solar panels were shredded, critical components were flung into the void, and the delicate, irreplaceable microcalorimeters were destroyed. The loss was a catastrophic blow to high-energy astrophysics. Experts reflect that Hitomi's full mission would have provided the first clear maps of how dark matter is distributed in galaxy clusters, a fundamental mystery of the cosmos. Its untimely death left a gaping void in our observational capabilities, delaying the next major advances in X-ray astronomy by nearly a decade. This devastating failure forced a global reckoning, a hard lesson on the absolute necessity of exhaustive, multi-layered testing for the complex software that governs a spacecraft's most basic function, its stability. How many other secrets of the dark universe were lost in that violent spin? This tragedy of a disoriented sentinel finds a strange parallel in another mission, one whose failure was rooted not in a software glitch, but in a simple, heartbreaking human miscalculation made back on Earth. The slow, silent death of a satellite can be as costly as a violent explosion. Russia's Elektro-L No. 1, launched in 2011, was a technological marvel designed to be a constant, unblinking eye on our planet's weather systems. Its multi-channel scanning unit was its revolutionary heart, a sensor that did not just see clouds but saw through them. By capturing images in multiple spectra of light, from visible to infrared, it could measure sea surface temperatures, track atmospheric moisture, and monitor the health of vegetation on a global scale, all in real time. This was the kind of rich, layered data that feeds directly into the complex computer models used to predict the path and intensity of hurricanes and typhoons. For a while, it worked as intended, providing a vital stream of information. But then, a gradual and irreversible decay began. The harsh space environment, with its relentless bombardment of solar radiation and extreme temperature swings, slowly degraded its sensitive electronics. Its vision blurred, its data stream became corrupted with noise, and eventually the advanced imaging capabilities that defined its mission faded into useless static. The satellite was left adrift, a blind sentinel in geostationary orbit. Meteorologists have since reflected on the quiet cost of this failure. With Elektro-L No. 1's full, continuous data feed, global weather models could have been significantly refined. The loss meant a crucial piece of the atmospheric puzzle was missing, potentially reducing the accuracy of long-range storm tracking for years. Its story is a sobering lesson in endurance, highlighting that getting a sophisticated machine to orbit is only half the battle. The true test is surviving there year after year. This gradual decline from the stresses of Earth orbit makes the sudden, complete disappearance of a probe in the deep black of interplanetary space all the more haunting. A sudden silence fell over the polar skies in 2005. NASA Image Satellite, the imager for Magnetosphere to Aurora global exploration, had spent 5 years revolutionizing our view of Earth's invisible shield. Its suite of neutral atom imagers worked like a form of cosmic echolocation, painting the first ever global pictures of our planet's vast magnetosphere. We could finally see this dynamic bubble, not just infer its presence as it was buffeted by the solar wind and sculpted into its teardrop shape. This was the ultimate space weather map, a live feed showing how energy from the sun was transferred into the system that protects all life on Earth. Then, without warning, the signal vanished. A single, crippling failure in the satellite's power system controller plunged it into darkness, severing that unprecedented view. The loss was immediate and profound. Space physicists quickly realized the practical consequences, as image-unique global perspective was the key to forecasting disruptive events. These are not just auroras, but powerful geomagnetic storms that can induce currents in power grids on Earth and fry the delicate electronics of satellites in orbit. Without image eyes on the entire system, our ability to predict the onset and severity of these storms was drastically reduced, leaving both our orbital infrastructure and terrestrial power networks more vulnerable. For 13 years, the satellite was a ghost, a forgotten sentinel tumbling silently in the void. Then, in a moment that seemed to defy physics itself, an amateur astronomer picked up a signal. Against all odds, Image had woken up. NASA engineers confirmed it was alive, its system somehow restored after over a decade of silence. For a few brief, exhilarating weeks, there was hope that the lost mission could be recovered, its revolutionary imaging brought back online. But the hope was fleeting. The satellite's vintage software and forgotten command protocols made full recovery impossible, and it soon fell silent once more, this time likely for good. That long, silent gap between loss and fleeting recovery underscores a deeper truth. Even when a lost technology is miraculously found, the data and the progress it represented are gone forever, creating a permanent scar in our scientific record. This poignant story of a brief, impossible return prepares us for a mission that was doomed not by a random failure, but by a fundamental flaw in its very design, an error that guaranteed its destruction from the moment it left the launch pad. The Arctic's fragile ice cap was about to have its vital signs monitored with an unprecedented precision. The European Space Agency's CryoSat-1 satellite, launched in 2005, carried a revolutionary instrument known as a synthetic aperture radar altimeter. This was no ordinary ice mapper. It was a device designed to measure the thickness of polar sea ice with an accuracy down to a single centimeter, and the elevation of vast ice sheets to within a few inches. This was the key to understanding not just the surface area of the ice, which other satellites could see, but its total volume, the true measure of its health and stability. Climate modelers were poised to receive a continuous, global stream of data that would finally settle urgent debates about the rate and impact of polar melting. But that stream of truth never flowed. A malfunction in the rocket's second stage left the spacecraft without the final push it needed to reach orbit. CryoSat-1, along with its unique and sensitive radar, plunged into the frigid waters of the Arctic Ocean, its mission ending just moments after it began. The loss was a devastating blow to climate science. Researchers have since reflected that the early, precise data from CryoSat 1 would have provided an unassailable baseline, a clear picture of ice volume at a critical tipping point. Without it, there was a 2-year gap in our understanding, a period of rapid change documented with less certainty. The agency's response was a testament to human resilience, swiftly approving and building CryoSat 2, which launched successfully 5 years later. Yet that delay had a real cost. The 2 years of lost measurements represent a missing chapter in the story of our changing planet, a chapter we can never rewrite. This story of a mechanical failure leading to a silent ocean stands in stark contrast to the next loss, where the enemy was not a faulty rocket, but an invisible flaw in the code that guided a spacecraft to its doom. Its sophisticated sensors were designed to read the moon's hidden history in a spectrum of light. India's Chandrayaan-1, launched in 2008, was far more than a simple orbital photographer. It carried a revolutionary instrument called the Moon Mineralogy Mapper, a device that did not just see the gray surface, but analyzed the specific colors of light reflected from it. Each mineral has a unique spectral fingerprint, and this mapper could identify them all, from olivine to feldspar, creating a complete geological map of the entire lunar surface. Even more critical was its radar, which peered into the permanent shadows of the polar craters, places where sunlight has not reached for billions of years. It was there, in those frigid, dark traps, that scientists hoped to find a treasure more valuable than any mineral, water ice. This was the mission's ultimate goal, to confirm the presence of the one resource that could sustain human life and produce rocket fuel, turning the moon from a destination into a waypoint. For 10 months, the data streamed in, revealing a moon far more complex and resource-rich than anyone had dreamed. Then, the harsh environment took its toll. The combined, relentless assault of solar radiation and extreme temperature swings, from searing heat in the sunlight to deep cold in the shadows, crippled the orbiter's systems. A series of cascading failures, starting with its star trackers used for navigation, led to a premature end. Communication was lost in August 2009, silencing its advanced sensors long before their planned mission was complete. Lunar geologists have since lamented the lost opportunity with profound clarity. A full mission duration would have provided a comprehensive, global confirmation of water ice deposits. Instead, the definitive proof had to wait for later missions, slowing the momentum for planning permanent lunar bases by several years. This failure is a masterclass in the brutal reality of cislunar space. It demonstrates that surviving the journey is only the first challenge. The real test is enduring in a realm that is constantly trying to break down even our most hardened machines. How do we build for permanence in a place that offers no quarter? This question of durability becomes even more urgent as we confront a mission that did not fail from a slow decay, but from a single, catastrophic misstep at the very moment it was supposed to achieve its goal. Deep in the classified world of military space, a different kind of loss unfolded. The United States National Reconnaissance Office launched a secretive satellite, known only as NRO-L-21, in the 1990s. This was no ordinary observatory. It was a testbed for revolutionary stealth technology. Its hull was coated in advanced materials designed to absorb radar waves, making it nearly invisible to the prying eyes of other nations. Even more impressive was its agile maneuvering system, a sophisticated propulsion unit that allowed it to change its orbit with a speed and subtlety that defied tracking. This combination of stealth and unpredictability was the holy grail for spy satellites, promising an unseen eye in the sky that could monitor global hotspots without ever being detected. But that promise shattered just after launch. A sudden and catastrophic propulsion anomaly, likely a valve failure or a fuel line rupture, left the satellite stranded in a useless orbit. Instead of slipping into the shadows, it became just another piece of space junk, its revolutionary coatings and agile thrusters rendered completely inert. The loss was profound, but its full impact remains locked behind vaults of secrecy. Defense analysts can only speculate that the successful deployment of NRO-L-21's technologies would have accelerated the development of America's next generation of reconnaissance platforms by a decade. The data lost in that single anomaly would have provided real-world validation of stealth in space, a priceless advantage in the silent, high-stakes chess game of orbital espionage. This failure is a stark reminder that in the realm of black-budget space programs, progress and setback are often hidden from public view, their true costs known only to a select few. The silent, sudden death of this stealth sentinel points to a growing danger in the skies above, one that would soon claim another victim in a much more public and destructive way. A silent enigma vanished from the tracking stations in 2011. China's Shijian 1104 was one piece of a larger puzzle, a satellite in a series designed for rapid technological experimentation. Its cargo was not for gazing at distant stars, but for helping the satellite itself find its way. It carried new, more sensitive star trackers, essentially celestial compasses that lock onto known star patterns to determine orientation with incredible precision. Alongside these were experimental communication payloads meant to refine its position through subtle signal shifts. This combination was a leap toward true autonomy, a future where satellites could navigate the complex traffic of Earth orbit without constant hand-holding from the ground. The sudden and complete loss of the satellite shortly after launch, due to an unknown anomaly, meant that all the performance data for these revolutionary systems vanished with it. Aerospace engineers deeply involved in navigation systems point to this specific loss as a critical setback. The real-world performance data from Shijian 1104 would have validated the new star tracker designs under actual orbital conditions, catching subtle flaws or confirming theoretical advantages. Without that practical feedback, the next generation of satellites had to rely on more conservative, proven designs or undergo their own lengthy and risky trial periods. This incident casts a stark light on the double-edged sword of rapid series development. Building satellites in batches allows for incremental upgrades, but it also means that a single, unexplained failure can compromise an entire pipeline of technological progress. How do you iterate and improve when the test article itself disappears without a trace? This quiet loss in low Earth orbit, a casualty of an unknown flaw, stands in sharp contrast to a mission whose failure was brutally, publicly clear, a spacecraft torn apart not by an anomaly but by a fundamental design error. A 9-meter-wide antenna once beamed knowledge directly into remote villages. NASA Applications Technology Satellite 6, launched in 1974, was a quiet revolutionary in the heavens. Its massive dish, the largest of its time, was not for listening to the cosmos, but for speaking to the people of Earth. It pioneered the very concept of direct broadcast, using its powerful signal to transmit educational television programs to small, simple ground receivers across the United States and later to villages in India. This was a profound leap, a vision of using space to bridge educational divides by bringing lessons in agriculture, health, and literacy directly to those who needed them most. The satellite was in essence a prototype for the entire global satellite television industry we know today. But that vision was cut short. a persistent and ultimately unfixable problem with its attitude control system. The delicate mechanism that keeps a satellite pointed steadily at its target began to degrade. The great antenna started to drift, its focused beam of information becoming unstable and unreliable. With no way to fully recover its precise orientation, the mission was decommissioned years ahead of schedule, its revolutionary broadcast capabilities silenced prematurely. Communication historians often reflect on the profound cost of that early end. A full operational lifespan for ATS-6 could have accelerated the global adoption of satellite-based media distribution by half a decade or more, demonstrating the social and economic power of direct-to-home broadcasting on a much wider scale. Its failure is a poignant lesson in the supporting technologies we often take for granted, the unsung systems like attitude control that must work perfectly for the revolutionary payload to function at all. The slow drift of this communications pioneer finds a dark parallel in a mission that did not fail from a gradual decay, but from a single, violent instant during a critical test. A satellite designed to stare directly at the sun was instead blinded by its own power supply. Russia's Koronas-Foton launched in 2009, a sophisticated observatory tasked with decoding the violent physics of our star. Its revolutionary instruments were tuned to the highest energies, including advanced gamma-ray detectors that could peer into the very heart of a solar flare as it erupted. These aren't just bursts of light, they are colossal releases of radiation, and understanding their exact composition is the key to predicting how they will interact with Earth's protective magnetic field and upper atmosphere. For months, the data streamed in, providing an unprecedented look at solar activity as the sun began to wake from a period of deep quiet. Then, the satellite began to falter. A slow, insidious degradation of its solar panels and battery system, exacerbated by the relentless thermal cycling of passing in and out of Earth's shadow, crippled the observatory. With its power dwindling, the sensitive gamma-ray detectors and other instruments were starved of energy, falling silent one by one until the entire satellite was declared lost. The consequence of that power failure was a blackout in our solar records. Space weather physicists point to this specific loss with deep regret. The continuous data from Koronas-Foton would have filled a critical gap in the solar cycle, providing a baseline of high-energy observations that was simply unavailable elsewhere. This missing information directly impacted the accuracy of space weather models, the very systems we rely on to warn of solar storms that can disrupt satellites, black out power grids, and endanger astronauts. The satellite's quiet demise is a masterclass in the hidden vulnerabilities of long-duration spaceflight. It demonstrates that even the most advanced scientific payload is utterly dependent on the mundane, relentless reliability of its electrical heart. This final loss to the slow drain of power brings our journey to its ultimate conclusion, a mission that carried not just instruments, but the very seeds of a future industry, only to be lost in the most fundamental of ways. Its radar eye could see through clouds and darkness, a revolutionary sentinel watching our planet's every move. The European Space Agency's Eris-1 satellite, launched in 1991, carried a synthetic aperture radar that fundamentally changed environmental science. Unlike optical cameras that need sunlight, this radar created its own illumination, bouncing microwave signals off the Earth's surface day and night, regardless of weather. It was the first of its kind to offer continuous, all-weather monitoring on a global scale, tracking the slow creep of glaciers, the subtle subsidence of land, and even the faint slicks of oil polluting the oceans. For 9 years, it provided an unblinking record of a changing world, its data forming the very bedrock of modern climate modeling. Then, the gyroscopes began to fail. These spinning wheels were the satellite's inner ear, its essential sense of balance. Without them, ERS-1 could no longer point its advanced radar with the razor precision required. In 2000, with its orientation degrading beyond recovery, the mission was terminated, and that revolutionary eye was closed forever. The loss of its continuous data stream was a quiet catastrophe for long-term studies. Climate scientists have since reflected that ERS-1's unique, uninterrupted record could have provided an even more definitive baseline for sea level rise and polar ice loss during a critical decade of change. Instead, the termination created a gap, a break in the story just as the plot was thickening. Its story is a powerful lesson in the importance of legacy. ERS-1 was a pioneer, the direct ancestor of today's sophisticated Earth observation fleets. Its early end forces us to ask a difficult question as we conclude this journey through loss. Are we truly building upon the foundations laid by these silent sentinels, or are we destined to repeat their fragile histories? The 28 missions we have explored were not merely failures, they were crossroads. Each one carried a piece of a possible future, a technology that could have reshaped our place in the cosmos. Their collective silence is a monument to ambition, to risk, and to the unforgiving physics of space. They remind us that every launch is a gamble, and every lost signal carries the echo of what might have been. Each of these 28 lost missions shares a common, haunting thread. They were not failures of ambition, but casualties of it, each one pushing the boundaries of what was technically possible at the time. The cost of this innovation is measured in more than just dollars. Experts in space policy often point out that every vanished probe represents a lost decade of scientific progress, a gap in our understanding of Martian climate, a delayed confirmation of water on the Moon, or a generation setback in our ability to predict solar storms. These were not merely broken machines, they were broken links in a chain of discovery. The disappearance of a single, specialized instrument, like that plasma spectrometer bound for Mars, could leave an entire field of research stumbling in the dark for years, forcing scientists to rely on inferences and simulations where they could have had hard, definitive data. This relentless pursuit of the revolutionary comes with immense risk, a truth etched into the history of every spacefaring nation. The frantic pressure of the Cold War, the shifting sands of political budgets, the simple, heartbreaking human miscalculation in a line of code, all of these terrestrial frailties were magnified a millionfold in the unforgiving theater of space. Out of this long, painful catalogue of loss, however, a new philosophy of spacecraft design was forged. The silent screams of these lost sentinels taught us a brutal but essential lesson. Redundancy is not a luxury, it is a necessity. Modern missions are now built with multiple backup systems, cross-checked flight software, and layers of fail-safes designed to prevent a single point of failure from dooming an entire program. The exhaustive testing that missions now undergo, from thermal vacuum chambers that simulate the extremes of space to vibration tables that mimic the violence of launch, is a direct legacy of these failures. We learned that to reach for the stars, we must first build for the inevitable stumble. This hard-won wisdom reveals a profound paradox at the heart of exploration. The very technologies that promise to open the cosmos, from ion engines to autonomous landers, are often the most fragile and the most likely to fail on their first outing. Yet it is this peril, this willingness to risk everything on an unproven idea, that ultimately drives humanity forward. Each lost blueprint and each silent satellite served as a stepping stone, its tragedy informing the triumph of the mission that followed. So what are the ultimate lessons carved from this legacy of silence? How have these ghosts of space missions past fundamentally reshaped our approach to the final frontier? And what does their collective story tell us about our own relentless drive to explore? These ghost missions speak a universal language of caution. The primary lesson echoing from every silent probe is the non-negotiable need for exhaustive, ruthless pre-launch testing. It is not enough for a system to work in a pristine laboratory. It must survive the violent shaking of a rocket launch, the brutal temperature swings of space, and the subtle creep of radiation. The catastrophic software error that doomed Hitomi was not a freak accident. It was a failure of imagination, a scenario that ground-based simulations simply did not anticipate. Similarly, the propulsion failure that stranded Phobos-Grunt points to a need for more robust component testing, shaking and baking every valve and fuel line beyond its expected limits. This philosophy of over-testing has now become a cornerstone of modern mission design, a direct and costly inheritance from these past failures. Another vital takeaway is the immense value of sharing the burden. When missions are funded and built by a single nation, a single budget cut or political shift can erase decades of work. International collaboration spreads both the financial risk and the pool of expertise, creating a more resilient path forward. Imagine if the revolutionary ion engine of Pioneer H had been a joint project between multiple space agencies. The loss of funding from one partner might not have been fatal, and the technology that could have traveled time to the outer planets might have been proven decades earlier. This collaborative model is now seen as essential for the most ambitious projects, from the International Space Station to the upcoming Mars sample return campaigns. It is a strategic acknowledgement that the cosmos is too vast and the risks too great for any one country to go it alone. Finally, these losses force us to design for resilience. Space is not just empty, it is actively hostile. Engineers now design for this reality, building in multiple layers of redundancy for critical systems like power and communications. The slow degradation of satellites like Elektro-L and the sudden power failure of GSat-6 taught us that a spacecraft's heart must have a backup, and a backup for the backup. This extends to software, where modern flight computers run in fault-tolerant pairs, constantly checking each other's work to prevent a single glitch from triggering a fatal spin. Implementing these hard-won lessons is our best defense against future losses, a way to ensure that the next generation of revolutionary technologies, from quantum communication satellites to interstellar probes, actually reach their potential and do not simply join the long list of silent sentinels. This reflection is not about dwelling on the past, but about building a more deliberate and secure future in space. It encourages a shift from a reactive posture, where we learn only after something breaks, to a proactive one, where we anticipate failure before the rocket ever leaves the pad. How might this newfound wisdom shape the next great leap, as we set our sights on permanent bases on the Moon and the first human footprints on Mars? The legacy of these vanished missions is not one of mere failure, but of blueprints passed forward. The very technologies lost to silence, from advanced ion propulsion to laser communication, are being resurrected with a new urgency. Look at NASA's Artemis program, which aims to return humans to the Moon. Its plans for a sustained lunar presence depend on technologies that echo those lost decades ago, like robust power systems and autonomous navigation, lessons written in the cosmic dust of missions like Schiaparelli and GSat-6A. Private ventures are joining this effort, building upon the foundational, and often fatal, work of pioneers like the Cosmos 1 solar sail. They are developing new propulsion methods and communication networks, striving to finally realize the potential that was snuffed out by a faulty rocket or a power glitch. This time, however, we are not starting from scratch. We are building on a foundation of hard-learned lessons. innovations in artificial intelligence now offer the promise of smarter, more resilient spacecraft. An AI pilot could have potentially recognized the sensor saturation that doomed Schiaparelli, overriding the flawed software and saving the landing. New materials science, informed by the lost data from missions like Chang'e 5T1, is creating composites and alloys that can better withstand the brutal extremes of radiation and temperature that slowly crippled probes like Elektro-L. These are not just incremental upgrades, they are transformative shields against the historic causes of mission loss. This evolving legacy actively inspires a new generation of engineers and scientists who study these failures not as tragedies, but as the essential textbooks of exploration. They learn that progress is not a straight line upward, but a path littered with setbacks, each one a crucial data point on the way to success. The story of Phobos-Grunt teaches the absolute necessity of propulsion reliability, while the Hitomi disaster underscores the life or death importance of flawless software. This collective wisdom is being encoded into the very DNA of modern spacecraft design. As we envision a future of lunar bases and crewed missions to Mars, the goal is to make such catastrophic losses rare. We are slowly creating a new normal where missions are expected to survive and even thrive for decades. This future is being built by acknowledging a profound and paradoxical truth that each failure, each silent sentinel, has fundamentally fueled our progress. The ghosts of these 28 missions are the unspoken partners in every new launch, their silence a constant reminder to build better, test harder, and dream smarter. These 28 silent journeys form a profound legacy of ambition etched against the stars. Each lost probe, from the earliest Soviet Mars attempts to the most modern communication satellites, was more than a machine, it was a vessel of revolutionary potential. They carried the seeds of technologies that could have reshaped our civilization, accelerating our reach across the solar system by a generation or more. This tapestry of loss is not a chronicle of defeat, but a masterclass in human resilience. It urges us to innovate with a newfound caution, to temper our brilliant ambition with meticulous perseverance, understanding that the path to the cosmos is paved with both triumph and invaluable failure. The stories of these ghost missions belong to all of us, and their lessons can inspire your own engagement with the final frontier. Consider how you might support the next great leap, whether through advocating for scientific funding, sharing these stories to educate others, or simply fostering a sense of wonder about our place in the universe. We would love to hear which of these lost technologies resonates most deeply with you. Was it the silent ion engine of Pioneer H, or the global eye of the lost climate satellite Glory? Share your thoughts in the comments below. If these mysteries of the cosmos captivate you, subscribe for more journeys into the unknown. Carry forward the enduring spirit of discovery that defines our species, and remember that every launch, whether it succeeds or falls silent, carries the collective dream of humanity